Hello everyone. We are going to solve an extra question. It have it has potential to be on the max exam. It has all the information that the max requires, and the idea is really fun. So the first thing is what is happening. So this green thing over here is a table or a block, and this is a rope over here. The length of a rope, this rope over here, is L. Part of this rope is x is in the side of this table, so it will end up, and there is no friction in this question. You can put friction later, okay? But what the thing is that there is gravity over here acting, okay? So there is gravity over here, okay? So this gravity will pull in this part over here, and then it will end up sliding all the way down. So questions is, how do you think the acceleration of this rope over here will behave, and what is the velocity in the end, like in the moment it ends up getting out, okay? This part over here gets here. So this is what we are going to answer. So for you to answer this types of question, like it's usually the same types of thinking you need to have. So first of all, and the rope has a uniform density, okay? The rope has a uniform density. So what does this mean? If the total mass, if the rope had total mass of m divided by L, this will be equal to the mass of this part over here, which I'm going to call it small mass B, divided by X, which is equal to small mass A divided by L minus X. So what is the mass of A? It's the mass of this part over here, okay? So this is what it means, that it has a uniform density, and this is mass of B. So this is going to help us even in the other thinking, like, because you might not be used for this types of question, but this types of question you are very used. This is mass of A, here are connected to a block, mass B, and there is gravity. This one you know how to solve, okay? And there is no mass in this string over here, so it's like I'm just thinking of this part over here. So let's think on this one over here, which is block B. What is the forces acting on it? Well, first of all, what proportion of its mass? So this mass B over here is equal to what? The mass B is equal to the big M multiplied by X divided by L. Okay, I just did this relation over here. Okay, so this we can use later. So what is the forces acting on this one? Well, this block over here, which is this part, we have gravity, its weight acting on it downwards, and we have now this, you can't forget there is another force acting on it, because here it's not obvious. Here you know it. Here you know that there is its weight over here and tension over here, and here there is also tension over here, okay? So its weight, the mass of B multiplied by gravity minus the tension, must be equal to what? Well, this is the force acting on it, right? The force resulting in this body is equal to what? Its mass multiplied by its acceleration, the resulting acceleration, okay? Notice this resulting acceleration is different than the gravity over here, because there is tension that's taking off of it. So it's mass B, and here the acceleration, which is the thing we want to find. Okay, now what about this part over here of the rope? This part, which represents like this block over here. What forces acts on it? Well, there is no friction over here, no friction. So the only force acting on this mass A is the tension, right? And now let's put over here a relation using this part over here due to the density and this. So the mass A is equal to what? L minus X multiplied by big M, which is the mass of the total rope, divided by L, okay, which is the length of the total rope, okay? So the mass tension is equal to mass of block A multiplied by what? By its acceleration. Now notice both of these accelerations are the same, because this accelerates downwards, this accelerates here. If it wasn't the same, you will end up stretching this rope, okay, and you can't stretch it, okay? So what's next? Well, let's put this T over here. So the mass of B multiplied by G minus the mass of A multiplied by this acceleration is equal to the mass of B multiplied by A. Now I'm going to put these values over here for the mass of B and for the mass of A, okay? So it's okay. So the mass of B is what? It is X multiplied by M divided by L, and here's G, minus the mass of M, it is L minus X multiplied by big M divided by L, and here multiplied by this A over here, equals the mass of B, X multiplied by M divided by L, okay, multiplied by this A over here. Now notice this mass of the rope over here, we have it everywhere and it will cut. This L, we will cut it, okay? So what do we end up getting? X multiplied by G minus L minus X multiplied by A equals XA, okay? So let's get this to the other side and this over here. So X multiplied by actually we don't need to get this over here because we want A, right? So what do we get over here? XA X, let's open this parenthesis over here. So actually don't need to open it yet. X multiplied by G is equal to XA. This whole thing will go to the other side plus L minus X multiplied by A, okay? So XG is equal to, now X here will minus X here, so we will have it AL, okay? So this acceleration is X, it is G divided by L multiplied by X. Now this expression over here is really interesting, because this expression tells you what? It tells you the acceleration with respect to X. Like the moment you know how much length of the rope is hanging out, you can immediately know the acceleration at that point. So what do I mean by this? What you have here is G, which is gravity constant. L is it doesn't change. L is the length of this rope over here, doesn't change. So the only thing that changes over here is X, okay? So from where to where does X change? X changes from 0 to L, right? Like, what does this mean? You can have 0, you can have it everything above the table, or you can have everything going downwards, okay? So over here, let's see if this thing over here functions, okay? So A is equal to G divided by LX. So what if everything is above the table? All the length is above the table. So X is equal to 0, okay? Because everything is on the table. So this is 0. A is equal to 0. Exactly, because everything is on the table, so you don't have acceleration. Now what if the whole rope, like the moment the whole rope over here what happens? Well, a is equal to g multiplied divided by l multiplied by x, but now x equals l, so we will multiply by l over here, cut, and we'll have that a equals g, which is exactly an object falls with the acceleration of gravity, because now there is nothing over here that he needs to push with it, right? So this clearly is functioning, and this is the expression. So now we want velocity. So how can we find this? Now for finding the velocity, we need to understand better what is that. One second, let me, it's just that I think it's going slowly. So you need to understand, like, the expression we found didn't depend on time. We usually find velocity, we find acceleration depending on time, right? The expression we usually write. We usually write what? Like v equals at, things like this. But here we don't have dependence on time. So how can you use this? What formula do you use when you don't have time? The famous one, right? The v final squared equals the v initial squared plus or minus, depending on the acceleration, to the acceleration, the variation of the space. Do you remember this? Now what's interesting about this? Let's see. The velocity initial is 0 because we are considering it sliding. We didn't give it velocity. So the v final is equal to the square root of 2a multiplied by the variation of space. So how can we find the variation of space? We have it right over here. What do I mean by this? This formula over here gives us exactly a graph, right? What do I mean? Let me see if I can. Yes, let's use this. And here, let's put it to 0 degrees. Let's put it over here. Okay. So how is this function over here? It's a linear function. It depends on x in a linear manner. So it goes like this. Okay? Where this over here is L, let me push it a bit more till here. Okay? This is big L, this is 0, and here is what? It's g, right? This is the acceleration, and here for x, for values of x, right? When x is L, we'll have the acceleration is g, okay? What about, for example, over here, when x, let's say small l, okay? For instance, small l. What acceleration are we going to have? Well, it's going to be j divided by l, small l, okay? So how can I find this multiplication over here, a multiplied by delta s? Well, it's the area of this graph over here. It is this area. Of course you can do it even with calculus. Yeah, you can do it. I think I didn't do it yet, but you can do it. So it's this area over here. So let's say, for instance, like if you let's say you had a part of the rope already out. Okay, let's say that in the initial x was equal to this small l, for example. Okay, so how much is the variation? How much a delta x? It is this area over here, because this is a, values of a, and this is l minus delta l. So what is this value over here? You can do it, you can divide it in triangles and rectangles and find this area, and you can do it with I don't remember the name of these things over here, but you have minus the sum of the two bases, which are GL divided by big L, and the second base is G, multiplied by the height. Okay, so just find this area over here and you will get this over here. This is the result over here. So let's write this in another way. Did I do it right? Yes. Yes. So we'll have minus 2. There's G over here, so J multiplied by L minus small l over here, multiplied by, here it is L plus small l divided by L. Okay, so what we get over here, now this over here, I think I solved yesterday a math question from the max just this way, I think, I'm not sure. So this multiplication over here, you will end up having L squared minus small l squared. Okay, if you do it, you will get this. It's a formula that is really useful to remember, but as it's not the focus of this subject, you can just, if you don't know, just multiply like this and you will get this. Okay, so minus J divided by L multiplied by L squared minus small l squared. Okay, so what is this that we just found? This is A multiplied by delta S. Okay, so we can use this in our formula over here. Notice that there is 2 over here that I will already cut with this 2 over here. Okay, so we'll have that the final velocity is equal to the square root of G divided by L, L squared minus small l squared. Okay, this is our speed. When is this our speed? It is in the moment that our rope is already sliding. Like if we had this rope over here with this part over here equals to small l, okay, and we left it over there like I made any rope. Okay, the moment everything now will start being vertical, this is your velocity. Okay, depending only on what, on the L that you put it in the initial and the whole length and G over here. Okay, so now the same idea, just so that we can fix it, this idea, what if we had this same rope but in an inclined plane? How can we solve it? Just let me see if this video is long. It's getting very long. So the thing over here is that it's the same things you do. What do I mean by this? I'm just going to find the acceleration, not going to find the velocity over here, but you can find it. So what do I mean? It is the same concept. So this is x. This is what? L minus x, because the whole length is L. Now the thing is, you need to find the forces applied in this. Now there is no friction over here. You can even put friction in other questions. You can put it like this. Maybe this is your block and here you put the rope. Okay, so how can you handle this one? So the force acting in this part, this force over here, minus the tension, because there is tension, attraction, I don't know, multiplied by this mass over here, this mass multiplied by its acceleration. But what is this force over here? The force applied in this part over here. Well, it's an inclined plane problem. Over here you have theta, and like if you had a block over here with mass m, this would be its weight. You need this component over here, okay, that will let him slide. What is this component? Well, this is theta also, right? Let me just try to do this better so that we can at least try to understand. Theta, we have a block over here this is the weight. This line is perpendicular to this plane over here. And what is that we want? We want this, the force in this direction. This angle over here is theta, right? So what is that we want? We want this part over here. So this is mg, which is the weight. So we want the parallel one. So it is mg sine theta. Okay, so we'll have that this mass over here, which is what? Well, it's notice another thing over here that we did once we cut it off. Notice that here we ended up cutting the m's and l's because the mass is proportional to the length, so we can just use the length. Okay, here. So you could say like the small m of b divided by x must be equal to the small m of a divided by l minus x, which is equal to m divided by big L. Like, you can do this, but in the end you will end up cutting these things because the mass is proportional to this length. Okay, so what I can use is the length from this mass over here. So x multiplied by g sine of theta minus the tension must be equal to what? To x, because it would be the mass of this b over here, multiplied by what? Its acceleration. Okay, now the tension must be equal to what? Now L minus x multiplied by what? Its acceleration. Now why L minus x? Because this mass is proportional, it's proportional to its length. Okay, so what can we do again over here? Xg sine of this angle, okay, minus L minus x acceleration a equals xa. Okay, just put the value of t over here. So xg sine of this angle is equal to xa plus L minus xa. Okay, so here the x will cut with this one. We'll have it is AL equal xg sine of the angle. So what we will end up getting is that a and this is just perfect, right? Because g sine of the angle divided by what? This is not small l over here, this is big L. This is the length. Okay, we didn't use anywhere small l over here. So divided by big L multiplied by what? By x. So notice this expression over here, we already made it, because this is the other question that we solved was a bit of a smaller version of this one. It was AGLX. What we found is sine of theta over here. Why there isn't any sine of theta in this one? Because our angle was 90 degrees. At this point over here it was 90 degrees, so the sine of this angle was 1. So notice, if this angle over here would open until 90 degrees, what would you get? A equals J divided by L, sine of 90 degrees 1, so you will get X. So this is a more general form for it. If you want to find the speed, the same thing, just because what? Because the graph now is still a linear function. All this is it doesn't vary. Sine of the angle is constant, J is constant, L is constant, so it only depends on X. Okay. And notice, what does happen when x is equal to L? Your acceleration is equal to J sine of the angle. Of course, it's the acceleration you get when you have the inclined plane problem. If you put a plane over here, it slides not with the acceleration of gravity, it slides with the acceleration of g sine of this angle over here. So you will get a graph like this, and then remember, in the end it will be some constant velocity, because once the whole rope is not constant velocity, constant acceleration here. This graph is acceleration by x. The time all the x is L, you don't have more rope, and your acceleration will be constant, with is g sine of the angle. Okay, in our problem, a vertical problem would be just g, so after that it will be just g over here. Okay, and you can find it by the area of this graph over here. So I think this is what I wanted to tell you about today. You can say, like, you can put the block over here, and this is the rope, and you can put friction, so you will have the only thing different is that you have this x multiplied by j minus the tension equals x multiplied by x acceleration, and here the difference will come, that it's not t equals to L minus x multiplied by the acceleration of this part, because you will have friction, so you will need to get off the friction, so it is minus the coefficient of friction multiplied by L minus x j must equal to L minus x a. Okay, so if there is friction, and then you solve for x and you isolate a, so you can find it. Okay, if the rope was like this, maybe like just hanging part of it over here, you will have weight over here and then tension over here, and so it will be the weight in the space of the friction. So but the idea is, you put the equations, you get off the traction, and then you isolate a. Once you isolate a, you find you will find that it's a linear function from 0 to L. It goes up linearly, and then it's a constant one, so you can find the graph, and then you can use that v squared is equal to 2a delta s, and if he gives you an initial velocity, you just put a plus over here. Okay, so this is it.